Hi, in this video, we want to take a look at the situation where we have some data and part of that data, a few data points, really have some problems with it. There's something going on with those observations. And what we want to do, we want to look at how does our model change when we include the bad data points and when we exclude the bad data points. Something I want to impress upon you is that the earlier something is in the modeling process, the more important it is. All right. So if you think about it, then the planning of data collection, which is really the first thing you do, that is going to be the most important step. Then data collection comes after that. Then we're actually going to be doing data prep, which is really the focus of this lecture, but only in one particular aspect of data prep. Then we do the modeling, then using the model. All right, why is it that I say that the earlier steps are more important? Well, that's because if we make a poor decision or we make a mistake or there's an error or something bad happens, an accident, then that mistake is going to propagate through the entire process. And so we have to make sure to protect ourselves, we have to make sure the early steps are very important to us. For this, quality data is more important than the actual model structure. That's something that contradicts a lot of YouTube videos, a lot of statisticians. That they emphasize the model structure and model selection, variable selection, stuff like that. That is not as important as having good quality data. Because if you don't have good quality data, you really can't do much with it. Think of it as like trying to build a house with poor quality materials. If I build a house with poor quality materials, it doesn't matter how good of a carpenter or how good of a mason I hire to build, the material just doesn't support good results. And it's just going to be that way. If I do a lousy job mixing concrete, no matter how well I pour that concrete, the foundation is going to stink. It's going to suck. There's just no ways around that. And really, our data is like the bricks and the concrete of our modeling. Okay, so remember, good data is critical to good model building. And bad data is worse than not having data at all. We are better off with the absence of information than bad information. All right, so let's go ahead and start doing some code. Let's go ahead and read in the data set. So once again, I'm using read.table. Here is the file path of my data. So remember, when I load in data, I really want to use this character string aspect. If you're using RStudio will let you click, make it real nice and easy. I promise you, when you get deeper into statistics, you don't want to be doing the clicking thing. You want to enter the entire file path or within the tail of the file path if you're using a working directory. The data has a header, so that's the row names. And then everything is numeric, so I just put in numeric to make it a little bit faster. If you specify the column classes, this can improve performance on your machine. Mainly with big data here, it doesn't really matter, honestly. All right, now let's go ahead and use the knitr cable function to take a look at the data. All right, so something about what I'm doing here. When you see this double colon means I'm saying, hey, within this package, the knitr package, execute the cable function. Why is this important? Well, R is open source. I mean, lots and lots and lots of people have built lots and lots of functions in R. And some of us have reused the same function names. And it's understandable if you start working through this stuff. Well, if this package uses a name for a function and this package says the same name but a different function, that means if I try to call one, I need to make sure I know which one I'm calling. Well, if I start loading my packages using the library or the require function, what can happen is that I can get package confusion. Usually the most recent package is the one that overrides, but sometimes it's not 100% clear. And so to be explicit, it's best practice to use the double colon notation. Also, you'll notice that I did not actually load the package. I only grabbed the function I want. This is very good practice because this prevents all the functions in knitr from creating package confusion with other packages. This is one aspect that Python does a lot better than R, by the way. Because, you know, like for pandas, you have to do pd dot whatever. All right, well, here is our data. We can see that we have bid price and coupon rate. And then we have case numbers. And the case number is just the row number for our situation. All right, now let's go ahead and build our model. So what we want to do, we want to use coupon rate to model bid price. Bid price is our target variable. Coupon rate is our predictor variable. And once again, I'm using the linear model function, LM. And this is from the bonds data. So I'm calling it LM bond. So in my convention of coding, I always do function name underscore something to describe what's going on. So it's a linear model using the bonds data set. All right, well, let's go ahead and plot our data. Let's make a scatter plot. Now, something I'm going to do that's different from what I've done in some other videos is I'm going to go through, I'm going to color my points. This is one of the things that I've learned is that can really add to the informative value of your visualizations by coloring your points. In my opinion, what you want to do, if it's important, you want to commit more aspects of your visualization to the plot of that one feature. So you know, here what I'm doing, I am the y coordinate, and actually, yeah, so bid price is my target variable. So what I'm going to do is I'm going to set up what this code does. This sets it up so that the color corresponds to the bid price. And so if I was to do further visualizations on, and you know, this will come up more when we start doing multiple linear regression, then I'll be able to see aspects of my target variable, which is the one that's most important to me, because that's the one I want to predict on. All right, so in this code, what I'm doing, first and foremost, I'm creating a color vector. And here I'm using the Viridis color palette. So that's in the Viridis package. And I'm using the Viridis function. And here I'm creating a color for each row, for each observation in the data set. And I'm just going, so I'm saying number of rows in the data set is how many colors I want. Okay. Well, how do we get this? What we're going to do is I need to connect the order of my data, the order of my target variables, to the colors. The colors are along a gradient as is. So here it spits them out in a way that goes from a specific color all the way to another color. It goes from purple to yellow. This color package is very nice in that it makes color of the rainbow, intensity, and grayscale all go along the same continuum. If you think about the rainbow colors, think about the intensity of yellow. Yellow is a very intense color. Well, where is that on the color palette? That's in the middle, right? If we go Roy G. Biv, yellow is somewhere in the middle. Well, if it's intense, someone might go, hey, because of intensity, I think that's the biggest. And people will make that mistake. So the rainbow color palette is not a good choice when you have continuous values. This package here is a good one for continuous values. Also, it's a very good palette for the colorblind. It doesn't support all versions of colorblindness, but it does a good job overall. And I have yet to find one that does it better. All right, so what I'm going to do, I'm going to take my target variable and I'm going to find the order of the order. The order is going to tell me which the very first. It's going to tell me which one is the largest, or it's going to go the smallest, then second smallest, third smallest. It's going to figure out going from least to greatest what the order is of that. Well, that's not quite what we want. What we want is we want the reverse of that. We want, so if one goes to the least, I want to switch it. I want the least to go to 1. And so I need an inverse permutation. So if you take in combinatorics, then you know all about permutations. If you haven't, don't worry about it. Just nod your head. Know that it's in the matrix package. Inverse permutation will do it for us. If you take abstract algebra, another good example of it, you'll deal with it up, down, left, and right, because in finite group theory, all groups are equivalent to a subset of a permutation group. All right, now what I'm going to do, I'm going to plot, I'm going to do a scatter plot where I have coupon rate as the X and my target variable is the Y. I go ahead and I label it, and I go ahead and just control the size of the plot. I put a plot character 19 to make it into a filled dot, and then I color it. And then I'm going to make an AB line using regression, linear modeled bonds, and then I'm going to make it a red line. And the reason why I chose red is because it's very distinct from the Viridis color palette. So let's go ahead and take a look. Okay, so look at this. Look at all these lines, all these points. These points look like they're doing a pretty good job of being on the line. That looks like a line overall. It's not a perfect line, but that's a line. Where's my regression line? My regression line is kind of tilted. See how it's kind of tilted like that? Well, what's going on is that these three data points over here are pulling the model over. Well, when we talk about leverage, data points that are the predictor variable value. So the data points that have predictor variable values that are farthest from central tendency have the most influence, the most leverage. So we can see that because of that, these three are pulling this entire line away from all of these points. All right, so this is kind of a problem because I know if I was to go through and I was to cover up those 3 points, if I was to go like this, cover it up, I will get a pretty good line, with this data. That's not what I have. So I need to do something about this because, if I'm going to launch this model, my career might rely on the output of this model. And I do not want to lose my job. If I want to lose my job, I'll just go and say harsh words to people and get myself fired or walk away. I don't want a failed model to be why I lose my job. All right, so let's go ahead and take a look at the model itself. Let's look at some aspects of it. So I'm going to go ahead and use the summary function. And the output of this, I can see that here's my range of residuals, -8 to 10.5. We can see that our coefficients are statistically significant. That's good. Our R squared is around 7.5 for both regular R squared and adjusted R squared. When these two values are far from each other, that's a sign of overfitting. Here they're close. Adjusted R squared will be less than multiple R squared. And my model is overall statistically significant overall. All right, well, something about this, if I look at this, so something I want you to impress upon you. If I see an R squared less than 0.7, it's useless for predictions. Just make that a blanket rule. That means that if it's less than 0.7, it is not useful for predictions. Now, why do I say 0.7? Well, if you think about like your matrix algebra, think about the dot product from calculus 3, and you think about how do you get the cosine of the angle between two vectors? Well, cosine of an angle between two vectors is equal to the dot product divided by the norm of each of the two vectors. Well, if you rearrange that a little bit, that cosine of the angle is equal to R squared. Okay, well, what is 45 degrees in cosine? It's about 0.7, roughly. Okay, so if I see less than 0.7 on the R squared, that means that angle is less than 45 degrees. Or excuse me, the angle is if R squared is less than 0.7, if it's less than 0.7, then the angle is greater than 45 degrees. I misspoke a moment ago. It's greater than 45 degrees, which means that the vectors are closer to perpendicular than they are to parallel, which means that I have no informative value. Or there is informative value, but for prediction, don't even attempt it. Here, this is kind of like, if I have to, I would use it. If I had to, I don't really want to. If I couldn't do better, then I might have to run with a 0.75 R squared if I get stuck into it. Sometimes it's just not in the data to get a better model. All right, let's take a look at the confidence intervals. All right, so here we can see that definitely statistically significant. So here we're going around maybe, averaging about 75, averaging about 3-ish, something like that. All right, now what we want to do now is that we want to get statistics on each individual data point in the model, and we want to use those statistics to identify problematic data. All right, so what I'm going to do is I'm going to take all of my data points and I'm going to compute some statistics with regard to the linear model on each of the individual data points. And these statistics I can use to guide me on what I should do about each data point. All right, so if this is a good idea, I'm going to see that these 3 points are going to get flagged, that something's going to come up about them. All right, so what can we pull out? We can pull out the leverage. The leverage comes from the hat matrix, so we call it hat values. So these are the values on the hat matrix diagonal. Here, these are our standard, gives us the standardized residuals. So standardized means subtract the mean, divide by the standard deviation. Residuals in ordinary least squares always have average 0, so all we're doing is divide by a standard deviation. Here, we're pulling the residual. So here, the residual function gives us the residuals from a model. So that's the difference between the model value and the observed value. The standardized residuals are the same as the output of this, but we divide by the standard deviation after we grab it. And Cook's distance is another way to check to see, basically where the distance, if it's far off, we have less faith in that being a good data point. Cook's distance, if it has a larger distance, we want to take a look at that point and maybe do something about it. All right, so now let's go ahead and print this so we can take a look. So all I did was I took the original data set, I tacked on the standardized residuals, the regular residuals, and Cook's distance. All right, so larger values in magnitude are the ones I'm worried about. Excuse me. So boring even on yawning. All right, now let's take a look at the residuals. There are going to be 3 types of residuals. First one are just a regular residuals. That's where I take the observed value minus the model value subtraction. The standardized residuals, I take those residuals and I divide by, I subtract the mean if it's a other type of model, and then I divide by a standard deviation. In regression, residuals always add up to 0, so the mean is 0. So we just divide by standard deviation. But if we're doing something like random forest, machine learning, neural networks, stuff like that, then we will subtract off the mean, then divide by standard deviation. There's another kind called the studentized residuals. Studentized residuals make the assumption that the residuals come from a normal distribution, mean 0, and constant variance. All right, if I have that, then I know the probability distribution that the residuals are coming from, and I can actually do a better job of standardizing them than the regular subtract the mean, divide by standard deviation. And in that case, I want to make some adjustments for what's going on. Now, here we're going to just use the standardized ones, just because there's less less stuff to do to get to them. If I'm doing regression, I want to use studentized residuals because it's a little bit easier to interpret. It's better to work with. As long as I have that assumption, that I have mean 0 and constant variance. If I don't, then standardized residuals is probably a good way to go. Here is like we're normalizing the distribution. All right, all types of regression models, whether it's machine learning or neural networks or gradient boosting, proximal centroid models, all of them have regular residuals and standardized residuals. But studentized residuals are special only to situations where we have, where we know what the theoretical distribution is. And that'll be mainly regression or linear regression, linear models. All right, so when we look at the standardized and studentized residuals, we want to take a look at it and we view it from the point of view that the residuals come from a standard normal distribution where I'm saying a 95% confidence interval is -2 to 2. Or not confidence interval, 95% observation interval is -2 to 2. All right, well, we know that there's some problems with our data points. When we looked at the previous scatter plot, we're like, hey, there's problems. I need to know which ones these are. So what I'm going to do, I'm going to plot the scatter plot just like I did. Actually, no, I'm going to plot the residuals. So here I'm going to plot the standardized residuals by the predictor variable. And I'm going to put -2 and 2 horizontal lines. And I'm going to go one step further. I'm going to label each point with the case number. Why is that? Why do I do that? Because that tells me which row the data is coming from. Now, when I do this, I can see very quickly that 4, 35, and 13 are those problematic data points. So when I look at it this way, I can see that 34 is right on that cusp of -2. I can see that 4 is actually within that -2 to 2 range. But when I look at the models, when I look at the original scatter plot, all of these points looked pretty good. It was these 3 that looked off. So these are the 3 that I'm worried about. All right, so what I'm going to do, I'm going to kick out these 3 points. I'm going to get rid of them, and then I'm going to rebuild my model. So what I want to do, I want to use the update function. Why am I using update? I don't want to rebuild my entire code. I just want to update. I want to change one special feature. So I go ahead and I do that, where I set subset equal to the data, the rows I want. So here I'm going 1 to the number of rows, and I'm saying, hey, get rid of 4, 13, 35. And I'm applying this to the linear model that we already built. Now let's go through and let's plot my data. And once again, I'm going to do this. Now, the difference this time is that I'm going to create a blue line for my new linear model. My linear model, the new one I call linear model bonds 2. I'm going to apply it in blue. And hey, that looks pretty good. So I kept, on the plot, I went ahead and I kept the points, and I kept the red line just to show, just so I can compare. And I can see that this blue line does a much better job fitting the data than the red line. Also, an issue is that when I look at the residuals, I don't want to see a pattern. I see a pattern right here. If you see a pattern, there's a problem with your residuals. All right, now if I take a look, we can see that our p-values are super small. The residuals are much smaller in magnitude. And now I've got nearly ideal R-squares. So I'm feeling pretty good about this model right now. And also the significance of the F-test is within machine accuracy. Okay, well, let's go ahead and let's plot the new standardized residuals, again, just to see how things have changed. So I'm using R standard to get the new residuals, and I'm just going to go ahead and plot them. I'm going to use the coupon rate, which is my predictor variable. I'm going to plot the new residuals. And I can see that almost every point is just within that -2 to 2 range. Now, something about this -2 to 2 range. We don't want to kick things out just to kick them out. We want to use our understanding of the situation to choose what to kick out. I kicked out the points that were off by themselves in that little cluster. And so if you remember, when I looked at the previous residual plot, this point was actually farther out than one of those 3 points, but I left it. Why did I leave it? Because that one was at least consistent with the rest of the data. And when I look here, I really don't see a problem with this. It looks like a random point. I mean, it does kind of look like maybe a sideways hourglass, but it's a small enough data set that I can't really say that that's good or bad. A good rule of thumb when I look at a scatter plot is if I could pick up one point and move it around and I come to a different conclusion on my plot, then I don't have a problem. So if I was to take, let's say, this point and I moved it over here, I would that hourglass image that I'm seeing in my eyes would disappear. Therefore, it's not an issue. All right, let's go ahead and plot Cook's distance. Now this is on the original data set, and we can see that the 3 points we got rid of were pretty far off. Now, when it comes to subsetting my data and removing data points, in general, we only remove data one time. If I'm going to remove data a second time, either I have to have a very good reason to, like I missed something that I should have caught on the first one, or possibly if I have big data and losing the data points isn't going to really impact anything, then it doesn't really matter. All right, there's also another way to pull out the influence of data points using influence measures, and it spits out a whole bunch for us. I went ahead and ran it. This is a faster way. This is a way that I would prefer to do this. We can see that it flagged observation 4, observation 13, and it flags observation 35 for us. So we can be pretty, so the system automatically flagged it. Now you'll notice that it's flagged, not pulled out, right? Remember, we always have to make, we need adult supervision whenever we run models. And adult supervision means I double check, do I have faith in that data point? So remember, if I'm treating this as a random variable, it is normal for me to have an extreme value here and there. And that might be normal, that might be a problem. All right, well, that's all I've got for you. I hope you're staying healthy. Take care and goodbye.